Imagine the Earth billions of years ago, a very different place, a fiery volcanic world. The surface was molten rock. The air was thick with noxious gases, no sign of life anywhere. This was our planet in its infancy. Slowly, Earth began to cool. The fiery surface solidified into the first rocks. Volcanoes still erupted, spewing lava and gases into the atmosphere. Water vapor condensed and fell as torrential rain, forming the first oceans. These early oceans were hot and acidic, a far cry from the life-giving waters we know today. Yet within this seemingly inhospitable environment, the stage was set for life to emerge. The very conditions that seemed so hostile held the key ingredients for life's beginnings. The building blocks of life, simple organic molecules, were starting to form. Scientists call the mixture of chemicals in early Earth's oceans the primordial soup. Imagine a warm pool of water rich in simple molecules like amino acids, the building blocks of proteins. These molecules formed spontaneously in the early Earth's atmosphere and rained down into the oceans. Lightning and ultraviolet radiation from the sun provided energy for these reactions to occur. This primordial soup, though seemingly simple, was a crucial step towards life. Within this chemical melting pot, more complex molecules began to assemble. These molecules interacted in ways that led to the formation of the first self-replicating molecules, the precursors to DNA and RNA. The exact details of how this happened are still debated. However, the primordial soup provides a compelling framework for understanding how inanimate matter could transition to the building blocks of life. One leading theory for the origin of life is called abiogenesis. Abiogenesis proposes that life arose gradually from non-living matter through a series of chemical reactions. Simple molecules assembled into more complex ones, eventually forming self-replicating molecules. These molecules, enclosed within simple membranes, became the first cells. Another theory suggests life may have originated in deep-sea hydrothermal vents. These vents release heat and chemicals from the Earth's interior. The unique conditions around these vents could have provided the energy and chemical building blocks needed for life to emerge. Regardless of how it started, life found a way. From these humble beginnings, life evolved and diversified, eventually giving rise to all the plants and animals we see today, including ourselves. Scientists have conducted experiments to recreate the conditions of early Earth and test theories of abiogenesis. The most famous of these is the Miller-Urey experiment. In 1952, Stanley Miller and Harold Urey simulated the early Earth's atmosphere. They filled a closed system with gases thought to be present at the time, added an electric spark to simulate lightning, and heated the mixture. Remarkably, after just a week, the experiment produced amino acids, demonstrating that the building blocks of life could form under early Earth conditions. This landmark experiment provided crucial support for the idea that life could arise from non-living matter. While we may never know exactly how life began on Earth, the quest to understand our origins continues to drive scientific inquiry. Each new discovery brings us closer to uncovering the secrets of life's beginnings and our place in the grand tapestry of the cosmos.